you want to know what is the injected power. Of course, these generators sometimes fail, right? So you describe each generator with this two-state unit Markov equation. And we're going to go over today in detail on how each of these units can be represented as this kind of a model, okay? Any questions about your homework that you have done? Your homework, previous one, and then today? I grade your homework, and I think you all are very creative. You have many different ways to solve the problems, okay? Quite challenging, takes me a lot of time to go over all the homework problems. But one interesting thing I want to mention is the conditional probability method. Okay, this is the one. The reason that I draw this diagram so that you can see clearly where the transition happens, okay? But in fact, what we want to, when you are solving like more than 3 components, like in your homework problem, you might not be able to write it out in a very clear ways. What we want to, essentially for conditional probability method, you wanted to calculate the frequency when the complicating component is working in one equation, which is, this is when the failure happens. In the green color denotes the upstates. The system is success. The red color explain the components, the whole system down, right? So you can see that when 2 is up, you have only 2 states, that is up, right? When 2 is down, you have 1 state. So in this picture, what you want to find out is the transition that happens given 2 is up, which is here coming down to the down state, and here going down to down state. So you can calculate this frequency. For when the component is down, you can calculate the frequency from this up to down to transition. When you calculate each of these sides, right, you can combine them, but then remember that there will always be another transition from your complicating component. Now, if there is no transition, it means that whatever this component, whether it's up or down, it doesn't affect the system failure at all. These 2 states will be the same, right? So there will be no difference. There will be no transition between these 2. Okay? But in most of the case, the transition, there would be a transition from given that the component is up and given that the component is down. That's why in the lecture I mentioned that you can calculate this probability. You see, the probability here is the probability of the component is, the system is up, given that 2 is up, minus the probability of system is up, given that 2 is down. So it's a subtraction of these 2 minus this which gives just this probability. On the other way, you might not want to work out the probability of success. You can also look at the probability of failure. Given that 2 is up, this is the probability of failure, 2 is up. And this is the probability of failure, given that 2 is down. In your common sense, which one will be bigger? When more components fail, the probability of failure should be higher, right? So when 2 is down, this probability of failure should be higher. The same goes when the probability of success as well, right? When you have more working components, it should be like this. So you can also calculate this probability of the state that makes a transition for the complicating component by looking at the failure probability. Okay. This one is the same as this picture. Okay. So this picture is trying to explain to you there would be like a big box, right? And then you can divide the state space, like this is your state space. You can divide your state space into 2 not overlapping subsets, okay, disjoint. One is when the component is up, and the other one is when it's down. Given when it's up, you would expect that the probability of success will be higher than when the component is down, okay. However, it might be cases that the 2 will be the same. That means that your component doesn't affect the system failure at all, okay? What I mean by finding the transition for the complicating component, in order to find the transition for the complicating component, you need to be able to extract the probability of the states that makes the transition. So how do you find the probability of the states that make the transition? It's this chunk, right? It's this one. So you can calculate by finding the probability of success of the 2 cases, or find the probability of failure of the 2 cases, and then subtract each other. Okay. So that will give you the frequency of this part, okay? And that's what is given here in this picture as well. So this one will be clearer, okay? So the idea here of all this is that the takeaways that you should understand is that you need to be able to describe the frequency. You need to be able to explain where this frequency happens, from what part to what part, okay? That's all. The frequency, okay, so let's come back to our outage model. The outage model that we are going through today, did I give you the homework for? Oh no, it's okay, it's assignment. Okay, next week. Next week we will do the simulation methods, but I'm going to move the time for you so that you can have more time for the quiz. Okay, maybe 30 minutes more. 30 minutes more. So, enough or not enough? Enough. Should be. Okay. So this, okay, the homework. This model, okay. I think I modified that in the other slide, so I'll show you later then. Okay, come back to where we left off with that. The goal of reliability measure. we have the mean time to failure, mean time to repair, mean time between failure, system availability, and frequency of failure. Of all these five, mean time to failure, mean time to repair, these are the reciprocal of the failure rate and the reciprocal of the repair rate. Okay? Mean time between failure is actually the reciprocal of the frequency. In overall, when we look at the observe the system, we will only see two states: success and then fail. So when we observe the system, we look at the time. Okay. The system availability is actually the probability. So the probability is given as mean time, right? It's just a summation of the time that you are in the success divided by mean time between failure, or actually mean time to failure divided by mean time to failure plus mean time to repair. Okay. So all these are all related. Again, cannot stress enough why we care about the frequency. Because if we care about just the probability, it will be misleading for your understanding of the system. Okay? So this is what I mentioned earlier. We have the analytical methods. Now we understand all these steps. I heard that some of you are a bit confused about the transition probability matrix and the transition rate matrix. Okay, transition probability matrix is in the discrete time case. You look at the Markov. That is the transition probability. So what's the difference between transition probability and transition rate? Transition probability is the probability of making the step, making the change. Transition rate is the rate at which you make the step change, okay? You make the state changes. When you look at the transition probability, all rows will be equals to 1. Because you're making the steps, and then this is a transition probability, right? You are here. There are only three possibilities. You can go from here to here, or here to here, or here to back. So because of those possibilities, all probability must sum up to 1. Okay. Whereas the transition rate, if you look at all rows, it will be summation will be equal to 0. This one, it comes up with the same concept as the probability, but you go back to the derivations. Okay, this is given like 5 or 6 weeks ago. So there is a difference between probability and the rate. But you can also simplify, or you can also use the rate and simplify it as a probability. That's what you did in your homework problem. Okay? So we went through the series and parallel network. We look at the condition probability. And we also revisit the cut set and tie set for the frequency failure calculation. Of all these methods, we assume that all failures are independent. Okay. the ideas of combining the series and parallel network based on the concept that you have a two-state diagram that has the upstate and downstate, just that, right? But what we are going to learn for today is alternative models, the models that will represent your system more, okay? All those models, the methods that can solve for the probability and frequency, okay, would be the state space approach and the frequency balance technique, because they are equivalent, they are the same. As long as you have a state transition diagram, as long as you write the transition rate matrix, you can always calculate the steady state probability, okay, as an exact solution, okay? So the concept of state transition diagram, you describe all the possibility of your component, your system in the state space. Two-state, we see it many times, and for you expand it, you have two components, each with two states. You can draw the state transition diagram like that. Now, for the outage model, when it's independent, it means that, as you can see, this is 1, 2, 3, 1 fail, 2 fail, 3 fail. Each of the failure of each of these components doesn't disturb the system at all. It goes by a steps. If one fail, two might fail, but the failure of component 1 doesn't change how the system works. System 2 and 3 will fail independently. So this is what we call the independent outage model. Each of these transitions describe when one component fails at a time, right? We've never seen a transition that goes like this. 1, 2, 3, fail together. But is it possible? Yes, it is. It is possible, right? But we don't do that. Why? Very complicated. But what we can do is we can represent those kind of failures. Okay? So for today, we will look at this kind of a dependent outage model. And the lecture today is not coming from the textbook, not coming from my textbook. It's coming from Professor Wen-Yuen Lee. Professor Wen-Yuen Lee is also very well known in reliability analysis. He's from Canada, and I gave you the reference at the end of the lecture, gave you the reference of the book. So he described these kind of models in detail, and I think it would help if you're doing research and if you're trying to find the right model for your problem. It can give you some of the motivation that you can dig deeper in the literature. I'm sure that there are many models that you can use in the literature. Okay? In the dependent model, there are two types that we will go into detail today. The first one is that more than one component fail at the same time with a common cause. Like what I show you right here. Common cause. What are those common causes that can happen in the system? How about the weather? the lightning. When the lightning strike, the components that are in the surrounding area will go out at the same time. Right? So those can be one cause of the common mode. And failure of one component may cause the other component's failure rate to be zero. It means that it's dependent. Once your circuit breaker trips, like the whole thing, even though it's working, but it's now out of your system. So it's dependent on one single component. So those kind of, we call it the dependent failure. What does it mean by that is that once it fails, there is no meaning to look at the rest of the state. Irrelevant. Don't look at that at all. If one fails, fix one first. 2 and 3 doesn't matter. Okay, so those are called the dependent failure. So we will look at the first. We will look at the individual outage model. It's not only 2 states as you see like that. There are more than a 2-state model. Okay, and then we'll look at the independent outage model. Dependent outage model. We will just spend a little bit of time just talking about the parameter estimation. But the parameter estimation will not be in the exam or in the quiz. Okay, this is just good to know. If you're working, you're doing research, you need to understand the importance of your data. Okay, so you need to analyze the data. You use that parameter estimation. And then we will look at the component failure model. And then I'll give you an example of those. Okay. So first, we have the individual outage models. In the individual outage models, we have like a forced outage, planned outage, semi-forced outage, and partial failure. So let's see what it means by that. When it's forced outage, you will hear when they talk about the generators being forced out, means that they go off for minutes. Okay. It can also happen that you might have some random failure. Okay. If it's a random occurrence that happens, you can use some kind of failure rate to model this occurrence. But actually, the random failure for the generator is quite small, quite rare. Okay. Mostly, the model for the generator will be in the types of this 2. Okay. First thing is it's repairable. What it means by repairable is this: when it fails, you fix it and then it comes up. The failure rates of these are the same. Chances that it will fail, the same. So the repairable looks something similar to the 2-state model. Because you look at the data and you see the data will look something like that picture. How long the generator worked and how long it takes for you to bring it back to system when it comes to repair. What it means by repairable is something like this. But what about the non-repairable? What is non-repairable? It happens when, you see, things get older, right? And power systems around the world, it has been there like hundreds of years. The main components in your system, not only a generator, but transformer, transmission lines, circuit breakers, all those things have age. Okay, like for a big components like transformers. Maybe half of this room, the size of a megawatts transformer that you see in the field, it costs millions of dollars. Okay. That's why this kind of aging failure is important for you to analyze those kind of components. It's an asset management, and it's not only for this kind of transformer. It can be applicable to any other systems. For example, transportation system, they also have some scheduled maintenance. They would also use this kind of model to represent. So the aging model, you can see it in the literature in a different field, but it all comes down to look something like a Markov model. So you have the working state, and then you have the states when it gets older. And then fail. So these are something like the aging failure, non-repairable. But in fact, when they study this kind of aging failure, what they look is that, should I do the inspection? And when do I do the inspection? When I observe the state here, should I do less inspection? Because when you inspect, sometimes you disturb the device. You might cause it to fail when you do the inspection. So those kind of analysis, you use this kind of model to analyze. Okay. This is a chance failure. Chance failure is quite similar to the random occurrence. And the thing is, when it comes to chance, you can't really fix it. For the non-repairable, if it's aging failure, you can try to fix, or you can try to make the device better. Okay. When we look at these kind of modeling, we try to mimic, we try to represent what actually happens in the system and try to represent it by some states. Okay. So these are the force outage model. Okay. The repairable force outage model, you have like a two-stage Markov model. This one I already explained. And how you can calculate this index is right here. For the non-repairable aging, this is hazard rate function, if you still remember. You see for the hazard rate function, when we represent the state transition diagram, we always look at this useful life that the transition rate is quite constant. That's how we can represent it by that diagram. But there are a lot more model, more interest, especially these days on this wear-out period, because we have been in operation for a very long time. Like in Thailand, it has been like 60, 70 years maybe in some of the components. So the analysis for this wear-out period is getting more and more popular. Okay, they will frame it as asset management, asset optimization. So those are in the area, in the research area of this. But how exactly do they work with this wear-out period? Actually, it's quite intuitively. If you have a function that is increasing with time, but you only have tools to represent a constant period, what do you do? What do you do with this? You guess? You make a step function. You make a step function out of it. So it means that at some point the transition will jump And that's how you represent it with this kind of model. Okay? So that is how we simplify this kind of wear-out period with the set function of the transition diagram. So now, let us look at the, so that is a forced outage. What about the planned outage? Okay, okay. When it's forced down, it means that the system requires it to shut it down, right? So there would be some failure rate for the force down in the previous case. And when it comes to sometimes you might have to do the maintenance as well. So you can have the outage in two different conditions, okay? And you can represent it as a three-stage Markov model. So when you're in the working, you might want to do some maintenance, or you might have some incidents that you have to, you fail according to some random failures. So this is a three-stage Markov model that you can use to represent one component. So it's not just up and down, just like that. Okay? But of course, when it comes to use this kind of model, the question that you need to ask is how you can come up with these parameters, right? So when you're using this kind of a model, it depends on whether you have enough knowledge, enough history, enough information of your system. For example, you need to differentiate when you collect the data, whether the device is down because it's forced to be out of the network, or is it down because it's on the maintenance schedule. So as long as you have those kind of information, you can use this model. Sometimes you can use the two-stage to approximate it as well. So you separate it, and then you find the probability of being up here multiplied by that, and that will give you. And actually, if you can write the Markov equations and then see when these two conditions can be approximated. Later on, we will write down the Markov equation using frequency balance technique to calculate the probability of being up right here. And we can calculate the probability here and probability here as well as the function of these rates, okay? For this, you already know how to write the probability. Okay. So sometimes you have the time delay in the outage. What it means is that it might not happen right away. The example given is like the transformer. The transformer, the bigger the transformer, they would have some medium inside. When I say medium, it means that it can be a gas or it can be oil to put inside the tank of the transformer. Like a big transformer, you see, it looks like a tank. Inside, they put oil in there. Okay. So that's why when it explodes, it can be a catastrophe. Okay. But the transformer that you see for the distribution system, normally they don't put oil in. Okay, it's a dry type. But for a big transformer, they have to put the oil in there. Why? Just to help release those kind of heat. Okay, to cool down the transformer. But the transformer inside, they have, do you know how the transformer is made? It has a coil, right? And coil itself has the paper as an insulation on the coil. And those paper is cellulose. It breaks down. It causes some kind of a sludge inside the oil. And those sludge, when it's kind of a, this is coil, and it causes some kind of a sludge. มันเหมือนกับเป็น it's like เป็นเศษผงอะนะ เป็น particle inside, and once this particle hit the outside of the transformer, it can cause failure. So what do they do is that they need to make sure that the oil is clean. So for the transformer itself, they would have a schedule to filter the oil. And once it's no longer helps to filter the oil, they change the oil. But those operations cost a lot of money. And that's why this kind of model helps to analyze when and what to do at what stage. Okay, I'll give you an example. In this case, if the transformer loses the oil, it might also cause some failure. So the way that we can represent the system is that you might have the system in the upstate, but then it starts to, it takes some time before it goes down. So they represent it as another state. Okay. Why do they need to explicitly represent it? Because in the state itself there is no time delay. Okay. So this is like a delay that can be represented by an extra state. Okay, by extra state. However, the reason they have to explicitly just have one state for this, because there is no time delay. But when we do the simulation in the next lecture, when we do the simulation, we can represent this kind of a time delay or anything in the simulation. Okay, okay, this might be a little bit confusing, but I'll just explain that if you don't have the Markov model here, if you have just up to the down state, you can also represent the time delay within this state without explicitly giving out this state. Okay. So this model, they use it for the short-term operation problem because it's like to represent the failure in the actual system. Now, the next one is the partial failure mode. Okay, this one is interesting because for this delay, for this semi-forced outage, it's like having a delay time right here from the up to the pre-outage, and then the pre-outage, and then you go to the force down, right? But for the partial failure mode, what does it mean is that if your component has some minor problem, some problem, that problem causes you to change the output of your capacity. For example, maybe your transformer has some problem with the oil. So you will say that, okay, it comes to the state that from the capacity of 100 megawatts that I can take care of, I can only look after 80 megawatts. So those are what we call the derated state. It's not like you are not supplying any megawatts, but you're doing it in a smaller amount. This one also applies to, for example, a generator. A generator might also have some problem too. So they will have this kind of a derated state that it can still operate. It doesn't fail yet, but it operates at a lower capacity. And that lower capacity, we call it the derated state. Okay, so this is a 3-state model. Now, when the derated state goes back to the up state, it's not very common. So what the model is saying is that it might be difficult to find the transition rate between the derated state to the up state, because when we do the repair, we will collect the data of the repair when it's down state to the up state, right? So usually you will wait until it fails and then you fix it. Okay? That's what it means by that. But that doesn't mean that you don't need to have, you cannot have this transition. Feel free to have all the transition. It depends on how you collect your data. When you collect the data, first of all, you need to ask your question, how many states do I have? How many states do I have? What are those states? If you are a generator, you ask how much capacity of the output do I generate? If you are a generator, right, you ask how much of the output that I generate. Let's see if I can generate 3, then that means you have 3 states. If I can generate 4, that means you have 4 states. If I can generate 5, that means I have 5 states. What next? After you have those states, look at the graph of the operation time. Let's say you have state 1, state 2, state 3, state 4, okay? Whatever states you have, observe your system. If you have state 1, let's see if you started, start observing from the system from state 1. You look at the time it's spent in state 1, and then see if it fails, how long it takes to fix, and then does it come back to state 1, it goes to state 2, 3, or maybe from 2 to 4, and then from 4 to 1, and then from 1 to 3, and then 3 to 2. This is how you observe your state, okay? And all these transitions that is here are the data that you collect for building your model, okay? So you need to be able to relate the model to the data and how you apply to your work. Okay? Okay, so this is the example. Now, for that partial failure, you can simplify it as using this picture. So what we do is we just ignore this transition completely. Okay? And how exactly can we, under what conditions can we ignore this transition? If we look at it, just look at this picture, okay, without writing equations, use our common sense. Common sense, you have common sense. We all have common sense. Without this transition, what it means? What it means is that if I sit here, if I'm at the derated state, okay, I have 2 options. I can go back with this, or I can go by this, right? 2 options. Only 2 options I have. If I can simplify here, it means that if I'm here, I am more likely to transit from here to here than to there. So it means that this rate should be higher than this, right? Right? Because if this is higher, I'm more likely to go here. I'm not going there when I'm right here. That's your common sense. Now, another common sense, from here to here, right? From down, you don't have this transition. Why? Because if you are here, where can you go? You can go up, or you can go to the derated state, right? And if I don't have this transition, it means that it's likely that I go to up states more than go here. So it means that this rate should be what? Much higher, right? Gives me more chances to go. So that is our common sense. Let's see by the example, by the equations, whether we are right with our common sense. Should be, right? So we look at what conditions should we have this. So we started off all of these problems with Markov state transition diagram. What you need to do is you started off with your transition rate matrix, right? How do I know it's a rate matrix? Because these are all the rates, okay? It's not probability, okay? So we know that it's a rate. Now that it's a rate, we write the transition rate. Look at the transition rate and check if your transition rate matrix is correct. All the rows must be 0, right? When you sum all the rows. Okay, so this is correct. Transition rate is from this state 1 to this state 2. Okay. So this is from up and then derate and down. Okay, up, derated, and down state. Okay. So that's how we can write the transition. I always remind myself by writing 1 and 2 and 3 so that I can write it correctly, 1, 2, 3. Doesn't matter if you name it 1, 2, 3 here, you could get a different transition rate matrix, okay? But the solution will be the same. Right? It's just a numbering that you have. So the probability of this will be 0 because at the steady state, no more change of the probability. These are the change of the probability. This is the rate, okay? It's not like in your transition probability. In the transition probability, you make another step. You're making another transition probability. You go to the same place because it's at steady state. But this is the transition rate. Okay, rate of change of the probability will be 0. Okay, that's why. So again, all these, they are linearly dependent. N-1 equation, not enough. So you need one more equation to make it solvable. One more equation is when P1 plus P2 plus P3 will be equals to 1, summation of that. So you replace one column with that, and then you invert the matrix. How did I do this? MATLAB. Okay, I'm not doing by hands. Okay, I use MATLAB. So you get the probability, like, oh, so fussy, and then that's how you have this 3-state Markov model. What about the 2-state? Now in this case, because it's easier, we can write the frequency balance technique. Okay, well, essentially it's the same thing. For the frequency, you look at the boundary 1, 2, and 3. So first draw the boundary of here. Make sure when you draw the boundary, you have a 2 separate disjoint boundary. Okay, 2 separate. In this case, you have P1 times lambda d will be equals to P2 times mu d, right? Because you draw the boundary of here. And then you have the boundary here, so P3 multiplied by mu equals to P1 multiplied by lambda. Another equation is that all these probability will be equals to 1. So you substitute this P2 by lambda d over mu d by P1 right here. And you substitute P3 by P1 right here. So you can solve for P1 and P2 and P3. So you get these. Okay. Doesn't look the same, right? So we need to force it to look the same. What did we do? We just multiply. Just, go directly, multiply this to both so that we can get the same kind of look. We want the up here to be mu d, and then down here to be this expression. So what do? We take all this here to have the expression. Now we are happy we have this expression. This expression is actually P1, right? P1 right here. So mu d, and then this expression, this one, right? So all this we have to simplify. All that we have to simplify. So essentially, what do? We know that if mu f much less than mu d, mu f is where? Mu f is much less than mu d. Lambda f right? I think I need to take a look at this thing. Can we take a break and then we'll come back? 30 minutes break, okay?
30 minutes.